Welcome to Math 1, Week 2. This week we're going to talk about polynomials, and we're going to do a continuous theme that we have in this class where we learn a new topic and then we play with it. And by play with it, we figure out how different concepts, in this case polynomials, interact. Add, subtract, multiply. The divide is a little bit different, and so we actually call dividing factoring, so that will be a new section. And then if we have time, we'll get to rational expression. Rational is a math keyword for fraction. So it kind of sounds safe and happy, but it really means putting a polynomial into a fraction. Okay, my first question is, what is a polynomial? And a polynomial is basically little groups of numbers and variables that are multiplied together. This is called a term. A term is any combination of letters and numbers multiplied. Terms are separated by pluses and minuses. We categorize the polynomial by its size. If we don't know the size, we call it a polynomial. So all 6 of my examples are in fact polynomials. We wouldn't say, because this is one term, it has a special name, and therefore it's no longer a polynomial. They all are in fact polynomials. It's kind of like saying students in a school. You're all students, whether you're an IT student, a design student, CJ, drafting, IT, you missed one. You still can all be called students. It's the same thing happens with polynomials. So the way I defined terms was groups of numbers and letters that are multiplied together, separated by pluses and minuses. So if we look at our first example, there are no pluses and minuses. So there is only one term. Here we have a plus and a minus. So we have 2 separators, which means we have 3 groupings, or 3 terms. Once again, we're back down to one term, as there are no pluses and minuses. Here we have 2 terms, separated by a minus. One term, even though there isn't any multiplication, even though there's no variable, even though there's no unknown, we still consider this a single term. And here we have 3 separators, so 4 terms. We could name all of these polynomials. That would not be very specific, and it wouldn't be giving us the full story. So when we have a small number of terms, we give our polynomial a more specific name. So one term, the word number 1 has a prefix of mono. And saying mono, and the word nomial is actually the word for term. Mononomial would be hard to say, so we cancel out one of the no's. And our single term is called a monomial. 3 terms, our prefix for 3 is tri, so this gives us a trinomial. Back to one term, monomial. 2 terms, our prefix for 2 is bi, like bicycle, so binomial. Monomial. Now once again, all of these could be called polynomial. Polynomial is just the generic for an unknown number of terms. But once we get up to more than 3 terms, we could continue with prefixes. There is a prefix for 4, it's quad. Quad means 4. However, we don't need that specificity. So when we get to 4 or more terms, we just break away from special names and give it the generic polynomial. Okay, so I'm going to discuss the leading coefficient. I have a row in my table for that, but it's important that you see the polynomials. So we will go through all of the leading coefficients, and then I'll get them written down so you can see how they translate to the table. A leading coefficient, which is our next table header, is the number in front of the largest degree term. And we will talk about degree in a minute. As it goes, I wrote all of these in descending order, so our term with the biggest degree will be our first term. So the leading coefficient just means the number, not the variable, not the unknown, but the number. So for this one, our leading coefficient is 3. For number 2, it's going to be 5. For number 3, this one gets kind of tricky, but last week we talked about the implied 1, and that's what we're going to use right here, is an implied 1. For number 4, it's going to be 2. For number 5, once again, no variables. It's still a term. It still has its leading coefficient, and it is in itself a leading coefficient. So our leading coefficient will be 5. And 6, we're back down to that tricky implied 1. So I'm going to get these numbers written over here. So 3, 5, 1, 2, 5, 6. Our next header is constant term. Constant term means a term without a variable. So if we look at our polynomials, and I hope you have them written down because I don't want the camera to be going back and forth really quickly. So I'm going to assume you have them written down so the camera can come with me. Our constant term is the number, is a term with a number and no unknowns. So for our first polynomial, our only term has a combination of numbers and letters, so there is no constant term. So I'm just going to use NA for not available or not applicable. For number 2, however, there is a constant term. A constant term is a term with a number, no variables. In the case of number 2, it is a -2. Our subtraction sign turns into a negative, and we get -2. For number 3, once again, we do not have a constant term, so we'll have an NA. And for number 4, NA. Our fifth example, the number 5, is a constant term. It is a constant term. It's a term that doesn't vary. That's why we define a constant term as having a number and no unknowns. So for number 5, our constant term is 5. And for number 6, it's a -5. Now for degree, the very last column in our table, a degree asks the question, how many unknowns does each term have? So for our first polynomial, which is just one term, the degree is pretty simple. We have 3x squared y, which gives us 2 unknown x's and an unknown y. So 1, 2, 3 unknowns. So this has a degree of 3. For our second polynomial, we have 3 terms, the 5x squared, the 4x, and the -2. Well, a constant term does not have a degree because there are no unknowns, and our degree has to do with unknowns. So this has 0 unknowns. This term has 1 unknown, the x. And this term, 5x squared, has 2 unknowns because the 5x squared is the same as 5xx. Our degree is not the sum of these 3. The degree is the single term in our polynomial that has the most unknowns about it. It's like that person in the back of the room that no one knows anything about. So this has a degree of 2. Our third polynomial, which is just x, has a degree of 1 because there's exactly 1 unknown there. Our next one, 2x cubed minus 5x, cubed would work better. 2x cubed has 3 unknowns. 5x has 1 unknown. 3 is bigger than 1, so our degree is 3. For number 5, which is 5, there is nothing we don't know about this polynomial. It is just the number 5. So the degree of unknown is 0. There is nothing we don't know about that polynomial. Our last example with our 4 terms is going to have a degree of 3, and it's your challenge to figure out why. It's possible. So now that we know what a polynomial is, we're going to start talking about how polynomials interact with each other. The first thing we're going to do is talk about adding and subtracting polynomials. We touched on this a little last week when we talked about algebraic expression and stacking our like terms and adding down. So we're going to formalize that a little with polynomials. This is a theme that we will talk about again in week 4 and in week 6. So it's it's good that we'll go a little bit slow and build this concept. So we're going to jump right into an example, and I'm going to use parentheses to define the two polynomials that I'm adding together. So I'm going to have 5x squared y plus 3xy minus 2 plus 6xy plus 10. So we have our trinomial added to a binomial. And we're going to combine them by looking in the second set of parentheses and stacking under the first set of parentheses and adding down. So if we look at our first term in our second polynomial, we have 6xy, and it's positive because there's nothing written in front of it. And we look and we, sure enough, have a term that has an x and a y, and we just stack that 6xy under our 3xy. Then we come back in and we see we have a 10, so we're going to stack that 10 under the 2, and we're going to add down. Our first term does not have a partner in crime, so we're just going to bring that value down, 5x squared y. 3 plus 6 is 9. The xy's just come along for the ride, so we have a plus 9xy. Over here, if we think of this as being an alley, and we're combining these two values, and pluses and minuses are on opposite side of the track of each other, like two gangs. They come into the alley, they're going to fight, the positives are going to win, and 8 of them are going to survive. So we have a plus 8. Hopefully part of adding our polynomials is review. Subtracting polynomials is pretty much the same process. What we're going to do is we're going to take control of our math, and we're going to turn the subtraction problem into addition so that we can subtract in the exact same manner that we add. So for our second example, I'm going to switch to subtraction. So I have 10x cubed plus 3x squared minus 5x plus 1 minus 2x cubed minus 3x plus 5. So what I'm going to do first is I want to turn this negative into a positive. Technically what I'm doing is I'm going to distribute the negative into the parentheses, which will turn the problem into addition. The way I'm going to write this is I'm just going to think of this subtraction becoming addition, and by turning this sign from a negative to a positive, I need to switch every sign in the second set of parentheses. My 2, which is positive, becomes negative. My 3, which was negative, becomes positive. My 5, which is positive, becomes negative. Once I have forced my subtraction problem to be changed into an addition problem, I can do the same process I did with the first example by stacking and adding down. So I take this minus 2x cubed, I find my x cubed term, and write it there. I have a positive 3x, which I'll put underneath my minus 5 3x. And then I have a negative 5, which will come under the 1. When I add down, 10 minus 2 is 8. The 3 does not have a partner. We have our two gangs. There are more negatives than positives, so the negatives are going to win. 2 are going to survive the battle. Once again, the negatives are going to win this battle. 4 of them will survive. And we have our answer. I'm going to do one more example of adding and subtracting, and then I'm going to move to multiplication, which is a much more interesting process. So for my third example,